What are you most afraid of when buying an EV? Definitely that it charges too slowly and doesn't run far enough. And that the battery level drops like a slide during high-speed cruising, right? Right now, sales reps from major automakers are frantically promoting 800 volts high voltage fast charging, claiming a 10-minute charge gives you 300 kilometers of range, even emphasizing that this is the absolute standard for next-gen EVs. But do you think this is simply taking to 400 volts batteries and connecting them in series, or just swapping in a thicker charging cable to get it done? Dead wrong. The real mastermind that allowed EVs to successfully leap from 400 volts to 800 volts and even caused a qualitative change in the entire car's power output, cooling efficiency, and cruising range is actually a semiconductor chip that is only the size of a fingernail, extremely precise and expensive. Without this chip, no matter how fast you charge, your car would just burn up from overheating. It wouldn't even be able to push the motor. Today, we are going to do a hardcore teardown of what is known as the EV's strongest heart, the super material, silicon carbide. In today's video, I'll first use the most straightforward physical principles and real tests, the data, to help you understand why the traditional 400 volts architecture has hit a dead end and why automakers have no choice but to invest heavily in upgrading to 800 volts. Next, we'll tear apart the EV's power core, the inverter, to see what the traditional silicon-based IGBT chip under 800 volts high voltage encounters in terms of fatal bottlenecks. Then, today's protagonist, silicon carbide, makes its debut. I'll bring out the concrete laboratory, data, and real-world test reports from authoritative organizations to tell you exactly why, in terms of conductivity, heat dissipation, and switching frequency, it completely crushes traditional silicon chips. Finally, we will also deeply explore the current manufacturing pain points of silicon carbide, why it is so expensive, and how it will completely change the future landscape of EV development. This entire video is packed with hardcore knowledge. I suggest you like and save it first. We'll start right away. Why has 400 volts reached its limit? The hard constraints of physics. To understand the greatness of silicon carbide, we must first figure out why automakers are upgrading to 800 volts at all costs. This all stems from consumers' range anxiety. As battery capacities get larger, if you want to shorten charging times, the only way is to increase charging power. We all learned in middle school physics a basic formula: power equals voltage multiplied by current P equals V asterisk I. In other words, if you want to push charging power from 150 kilowatts to 350 kilowatts or even higher, you either increase the current or increase the voltage. Under the past 400 volts architecture, automakers could only choose to desperately increase current. But this hits a physical wall known as Joule's law. Joule's law tells us the heating power of a conductor is proportional to the square of the current P underscore loss equals I to R equals I to R. If you double the current, the heat generation directly quadruples. To solve this terrifying waste heat, the charging cables and the wiring inside the car must be made super thick, stuffed full of heavy pure copper. Even so, when the current surges past 500 amps, standard charging gun cables, if not equipped with complex liquid cooling systems, will heat up to the point of melting within minutes. At the same time, the thick wiring harnesses inside the car also bring a massive weight burden. The heavier the car, the more power it consumes. This completely violates the EV's original intention of pursuing high range. So, engineers changed their thinking. Since we can't increase current anymore, let's double the voltage. When the system voltage is raised from 400 volts to 800 volts, under the same high-power charging, the current can simply be halved. Halving the current means that line heating instantly drops to 1/4 of its original level. The benefits this brings are incredibly dramatic. Take the Porsche Taycan, the world's first mass-produced car to adopt the 800 volts architecture. For example, according to official data, just because the current is halved, the cross-sectional area of the high-voltage wiring harness inside the car can be drastically reduced. The entire car's pure copper wiring harness weight was directly reduced by nearly 30 kilograms, a weight reduction of 30 kilograms. This is a massive advantage for vehicle handling and range. Moreover, the pressure on the cooling system is greatly eased. so that when the battery undergoes continuous high-intensity discharge, or supercharging, it won't easily trigger thermal throttling protection. 800 volts looks absolutely perfect, right? But when engineers were preparing to power up 800 volts, a core component inside the car lets out a wail. That was the inverter. The inverter, the limit of the traditional silicon chip IGBT. Many people think the core of an EV is just the battery and motor. Actually, there is an extremely crucial role in between called the inverter. The battery outputs direct current DC, but the EV's drive motor needs alternating current AC with constantly changing frequency and voltage to precisely control RPM and torque. The inverter's job is to use the semiconductor switches inside, switching frantically at speeds of thousands to tens of thousands of times per second to chop the DC into AC. This process is called pulse width modulation (PWM). In the 400 volts era, the inverter primarily uses components made of traditional silicon materials called IGBT insulated gate bipolar transistor. The IGBT acts like a water pipe valve. It worked reasonably well in a 400 volt environment, but it has two fatal flaws. First is conduction loss. When current flows through it, there's a fixed voltage drop, generating heat. Second, and more severe, is switching loss. When the IGBT turns off, the current doesn't disappear instantly. Instead, there's a sluggish tail current. You can imagine it like turning off a faucet. The water doesn't stop immediately, but still drips a few more times. When the inverter has to switch on and off 10,000 times a second, 10 kilohertz, each sluggish tail current converts into a massive amount of waste heat. At 400 volts, this amount of heat can still be suppressed by the liquid cooling system. But if you push the voltage up to 800 volts, the IGBT switching loss skyrockets exponentially. Not only does it generate shockingly high temperatures, it might even be directly pierced and destroyed because it can withstand the high voltage. To make the IGBT survive 800 volts, engineers could only make it larger and thicker. But this would further reduce the switching speed and increase losses. This formed an unsolvable endless loop. At this time, the industry realized that traditional silicon materials had approached their physical limits. We needed an entirely new super material, the dimensional strike of silicon carbide SiC. Right at this moment, the third-generation semiconductor material, silicon carbide, SiC officially took over the battlefield. Silicon carbide is a crystal structure formed by alternating silicon and carbon atoms. It is a wide bandgap semiconductor. We don't need to dive deep into overly complex quantum physics. You just need to look at a few sets of brutal laboratory comparison data, and you'll understand why silicon carbide is a dimensional strike against traditional silicon chips. First, break down electric field strength. The critical breakdown electric field of silicon carbide is about 3.0 megavolts per centimeter, while traditional silicon is only 0.3 megavolts per centimeter, a full 10 times difference. What does this mean? This means to withstand the same high voltage of 800 volts or even 1,200 volts, the thickness of a silicon carbide chip only needs to be 1/10 of a traditional silicon chip. With a thinner chip, the resistance when current passes through on resistance drops significantly. Conduction loss plummets directly. Second, electron saturation drift velocity. Silicon carbide is more than double that of silicon. This means it doesn't have the annoying tail current problem of IGBTs. When a silicon carbide MOSFET turns off, it cuts off cleanly and instantly. This allows its switching speed to easily reach several times or even over 10 times that of an IGBT. Third, thermal conductivity. The thermal conductivity of SiC is almost 3 times that of traditional silicon. This means not only does it generate less heat itself, even if it does heat up, it can conduct that heat away 3 times faster. It can even operate stably under extreme high temperatures exceeding 200 degrees Celsius. Whereas traditional silicon chips are ready to be scrapped once they exceed 150 degrees. Combining these 3 characteristics together, silicon carbide's performance in EVs is like using a cheat code. Not only can it easily withstand the 800 volts high voltage, it also maintains extremely low energy loss under ultra-high voltage. This is also why all automakers wanting to build an 800 volts architecture must abandon IGBT and fully embrace silicon carbide. Lab data and real car validation. Just how much power can it save? We've talked so much theory, but what about the actual combat data? Is silicon carbide really that magical? We can look at the comparative experimental data from renowned auto parts giant Delphi, now part of BorgWarner, and Microelectronics on the exact same motor drive test platform. When the switching frequency is set to 10 kHz, the overall energy loss of a SiC inverter, it is massively reduced by 70 to 80% compared to a traditional IGBT inverter. This reduction in losses is especially obvious at low loads. What is a low load? When you are doing stop-and-go driving in the city or cruising at a constant speed on the highway, and the motor doesn't need to exert full power, that is a low load. This actually accounts for over 90% of our daily driving time. Experimental data shows that in the light load range, the conversion efficiency of a traditional IGBT inverter will drop to roughly 92% to 94%, but a silicon carbide inverter can still firmly maintain a terrifying efficiency of 98% or even 99%. This reflects astoundingly on the actual vehicle range. Comprehensive test data from the US EPA and Europe's WLTP indicates that simply by swapping the inverter from IGBT to silicon carbide, under the premise of not increasing battery capacity at all, an EV's comprehensive range can increase out of thin air by 5% to 8%. If your original car could run 500 kilometers, swapping to SiC makes it capable of running 540 kilometers directly. This saved electricity is equivalent to saving automakers the cost of tens of kilograms of expensive lithium batteries. And that's not all. Silicon carbide's ultra-high switching frequency can easily reach 20 kHz or even higher. This is also a huge boon for the motor, because the higher the switching frequency, the closer the AC waveform output to the motor is to a perfect sine wave. Real-world analysis by foreign auto media cars and drivers and ADAC points out that a high-frequency, smooth waveform can substantially reduce iron loss and copper loss inside the motor, making the motor run smoother and with less high-frequency noise. Moreover, heat generation at higher PMIs is significantly reduced. This is why EVs equipped with silicon carbide during continuous highway cruising exhibits much more solid power consumption performance than traditional EVs. You won't have that situation where power consumption collapses as soon as you hit 120 kilometers per hour. As early as 2018, the Tesla Model 3, relying on keen engineering intuition, became the world's first mass-produced cars to deploy SiC MOSFETs on a large scale in its main inverter. Although it was still a 400 volts architecture back then, it was precisely this silicon carbide heart that allowed the Model 3's power consumption performance to wipe the floor with all the traditional German automakers of that time. And now, entering the 800 volts era, silicon carbide is no longer an optional advantage, but an essential standard feature, including Hyundai's EG-MP platform like the Ioniq 5, Porsche's PP platform, and even Lucid Air's exaggerated 900 volts plus system, all completely rely on silicon carbide to hold everything together. The silicon carbide production hell. Why is it so expensive? Since silicon carbide is so amazing, why until now are there still many budget EVs reluctant to use it, even only using SiC for the rear motor, while the front motor still uses the old IGBT? The answer is very simple, yet very cruel, because it is simply too hard to make and too expensive. Currently, a silicon carbide power module of the same grade, it costs about 3 to 5 times as much as a traditional silicon IGBT. If a dual motor EV goes all in on silicon carbide, the inverter cost alone might surge by several hundred US. And this exorbitant cost primarily comes from the silicon carbide wafers practically hull-level manufacturing difficulty. For traditional silicon wafers, we use the Czochralski method, slowly pulling an ingot out of melted liquid silicon. The growth speed is very fast, growing several centimeters in an hour, and can easily yield 12-inch or even larger wafers. However, silicon carbide has no liquid state. When heated under atmospheric pressure, it sublimates directly from a solid to a gas. Therefore, to manufacture silicon carbide wafers, one must use the extremely harsh physical vapor transport PVT method. What kind of process is this? You have to be at 2,500 degrees Celsius or higher in a high-temperature sealed graphite crucible. Let the SiC powder at the bottom sublimate into gas, and then let the gas slowly drift to the seeded crystal at the top to recrystallize and deposit. This process is like planting an extremely delicate tree inside a volcano crater. if the temperature is even slightly uneven, or if a single speck of dust gets in. Defects will form in the crystal lattice, and the entire wafer is ruined. Even more frustrating is its growth rate. Traditional silicon grows several centimeters an hour. Silicon carbide bakes in a 2,500-degree high-temperature furnace all day long, for 7 days and 7 nights without rest. And the ingot only grows a mere 1 to 2 centimeters. Processing it after it's grown is an even bigger nightmare. The Mohs hardness of silicon carbide reaches 9.2, second only to diamonds, making it one of the hardest substances in nature. A traditional diamond wire saw slicing through traditional silicon ingots is like cutting tofu. But using it to cut silicon carbide is like sawing rock. The cutting speed is extremely slow, and the material lost during the cutting process, kerf loss, is as high as 1/4 of the ingot's volume. Slow growth, high defect rate, and extremely material-consuming cutting. These 3 major pain points stack together, creating the persistently sky-high price of silicon carbide. Currently, the global high-quality silicon carbide production capacity is almost entirely tightly grasped by international giants like Wolfspeed, Microelectronics, and Infineon. The speed of capacity expansion is far behind the explosive demand for EVs, embracing the ultimate form of the future. Despite the immense difficulties in manufacturing, the sheer force of the semiconductor industry is taking effect. Major foundries are pouring all their efforts into conquering the mass production technology of 8-inch silicon carbide wafers and developing new processes like laser cutting to reduce losses. According to industry forecasts, within the next 3 to 5 years, as yields improve and economies of scale kick in, the cost of silicon carbide will experience a cliff-like drop. When the cost of silicon carbide drops to the sweet spot for widespread adoption, that is when the 800-volt architecture will completely dominate the market. By then, even entry-level commuter cars costing a few $100,000 NT will be able to enjoy the ultimate experience of charging for 5 minutes and commuting for an entire week. The cooling system inside the car can be made much smaller. The cabin space will become larger. The volume of the motor can shrink. Yet the horsepower it bursts out will be even more astounding. From 400 volts to 800 volts. On the surface, it just looks like a number doubling on a spec sheet. But behind it is a comprehensive technological revolution spanning from material science, thermodynamics, to power electronics. Silicon carbide, this super material born under extreme high temperatures and pressures, is quietly overturning our understanding of automobiles. Next time you walk into a showroom, looking at those avant-garde EVs, and listening to the sales rep boasting about ultra-fast charging technology, you can smile knowingly to yourself, because you already know that all of this magic comes from that heart hidden deep within the metal shell, the powerful and calm silicon carbide heart. If today's hardcore technical teardown has helped you unlock the engineering secrets behind EVs, don't forget to like this video, subscribe, and share it with friends interested in electric vehicles. Your support is our greatest motivation to produce in-depth content. See you next time!